Let's look at inverse functions. On our agenda, I'm going to give you 2 do now problems for check-in. We'll define our functions and inverses and notation. We're going to look at finding inverse of points, lines, quadratics, and we'll have a special challenge at the end. We're going to algebraically verify if they're inverses and then graphically prove that they are inverses. So to get ready, you're going to need paper, pencil, and Desmos. This lesson is a little bit longer and a little bit tougher, but we can do it. Be sure to pause and try some problems. Here's your do now problem. Try both of them, hit pause, and then come back for your answers. In the first do now problem, I want you to describe the transformation in words. So everything has a certain effect. What does the negative do? What does the 3 do? What does the plus 2 do? And what does the negative 5 do? You have to use words to describe all of that. So the negative means it's reflected over x. The 3 means it's vertically stretched by a factor of 3 because it's outside the parentheses. X minus 2 means it's going to go left 2, and then the minus 5 at the end is going to affect y, so it's going to go down 5 units. When we graph the piecewise, we look first and see that I have a quadratic and a line, so just keep that in mind. I'm going to look at my restriction, and I'm only going to use my quadratic when it's less than 1. So think about graphing that first. This is a quadratic that has the plus 3, so it's shifted up 3. It's vertically stretched by 2, so I can use my step pattern to go up 2 and to the right 1, and up 2 and to the left 1 because of symmetry. And I'm only using it when x is less than 1, so it gets an open circle, and I'm using it to the left. For my line, I can take 1 and I can plug it back in there. 2 times 1 is 2 plus 1 is 3. So I'm at this point. It is a closed circle, and I move my slope, and I have that line, and you have graphed that piecewise function. Let's start inverses. So an inverse relation is the set of ordered pairs obtained by exchanging the coordinates of each ordered pair. When you think inverse, you should be thinking, I need to switch the x and the y. Just a careful note, you switch x and y if it's just equations and just numbers. If it's a word problem, do not switch the variables. So if x represents t-shirts and y represents sweatshirts, you can't switch them because they already have some representation. So you would just solve for the other variable. Let's start with the inverse of points. So I'm going to graph my points and label them like we did in geometry. So A is 1, 3, B is negative 5, 1, and C is negative 2, negative 4. When I find my inverses, I'm going to create a new point A prime. And remember, with inverse, you're switching your x and y, so my point becomes 3, 1 for A prime. And B prime becomes 1, negative 5. And C prime becomes negative 4, negative 2. And take a minute and see what you notice. I went from A to A prime, B to B prime, C to C prime. It's kind of this diagonal action going on, and if we look closer at it, it is in fact reflected over this diagonal line, y equals x. That is going to be true of all of our inverses. Inverses will always be reflected over the line y equals x. Let's move on to finding the inverse of an equation, and we'll start with a line. So when we're thinking inverse, we're going to switch our x and our y, but first I want you to notice our function notation. So f of x means y, and f to the negative 1 of x means inverse, and that's what we're trying to find. So I'm going to switch my x and my y. So this becomes x equals 2y minus 3, and I want to resolve for y. So I'm going to add the 3 over. I'm going to switch it around because I prefer my variable on the left, and I'm going to divide by 2. I would accept that equation, and I would also accept when you separate the fraction. Both of those are the same thing, and we can say that that is my inverse. So you're going to switch the x and y, resolve for y, and you'll get the inverse. Take a minute to hit pause, and I would like you to graph both of them and see what you notice. My yellow line, my yellow equation is this one, and my blue equation is this one, and they are in fact reflected over that purple dotted y equals x line. So graphically, it checks out. Let's try to find the inverse of a quadratic. So I want to switch my x and my y, and I want to resolve for y. So I'm going to subtract 1 from both sides, and I have the y squared. Remember, to undo something that's squared, you have to take the square root, and remember, when you're taking the square root, you need to remember the plus or minus. So I'm going to have plus or minus the square root of x minus 1 equals y. So let's think about what that's going to look like when we graph it. If I graph the parabola, that is a parabola that's shifted up 1, and it has the regular step pattern. And then if I were to graph the positive square root, that would be this orange piece, and the negative square root would be this blue piece. You can see that together they are going to fail that vertical line test. So this sideways parabola is not a function, therefore we can't graph that whole thing. So I want to think and choose, and you can choose either one. I always like to choose the positive. So I'm going to graph my inverse as only the positive square root of x minus 1, which means only this orange piece, not this blue piece. Well, if I'm doing that, then I have to go back and I have to restrict my original parabola, because it is that full U shape, and I can't use the whole thing and then reflect it over the line and get part of the thing. So I have to restrict my domain. So I only want to use this piece here from here up. So it's very important to know what your vertex is, and in this case it is 0, 1. So I want to use this parabola when x is greater than or equal to 0. That is my restriction to the domain. Let's see what that looks like a little. So I'm only using the positive, not the negative. I've graphed the positive as the square root with the orange. I would have my full parabola, but I'm going to restrict it, so I'm only graphing that when x is greater than or equal to 0, and I have this purple piece. And now you can see graphically that they are inverses of each other. Let's try this one. This is a little tough. I'm going to allow you to try it on your own first. So hit pause. If you need a little help, may I suggest completing the square? And now I'm going to do it with you. So I'm going to switch my x and my y. And I suggested completing the square. So I have y squared and y. So I want to make this right-hand side a perfect square trinomial. It isn't right now with the 10, because 10 is not a perfect square. So I'm going to subtract the 10 over. And I'm going to open a blank, and then y squared plus 3y, and I'm going to open a blank. And I still open the blanks just so I remember to add to both sides. So the key piece of completing the square is taking half of b and squaring it and adding it to both sides. So that means my b value is 3, and I'm going to add 3 squared to both sides. I'm going to square it over on this side. So now my right-hand side is a perfect square trinomial. My first term is a perfect square, my last term is a perfect square. So I'm going to factor that, and it's going to factor to y, and then whatever the sign of b is, y plus 3 halves squared. The left side is a little trickier, but we can make a common denominator with negative 10. So that would become negative 40 over 4 plus 9/4. So that becomes x minus 31 over 4, and I prefer to stay with the fractions. So again, we're going to keep our eye on that y. That's what we're trying to solve for. So at this point, I want to take the square root of both sides. Square root, remember the plus or minus. So I now have plus or minus the square root of x minus 31/4 equals y plus 3 halves. We are almost there. There's one more step. I want to undo the plus 32, plus 3 halves. So I have y equals negative 3 halves plus or minus the square root of x minus 31/4. That is the inverse of my original function. Now let's think about the graph. This gets a little tricky because we have our fraction. So let me start fresh, and we have my inverse as y equals negative 3 halves. I am just going to do the plus version, x minus 31/4. And I'm going to think about transformations when I'm trying to graph this. By the way, 31/4 is just a little bit less than 8. So if I'm graphing this with my square root, this is going to shift to the right a little less than 8, and it's going to go down 1.5. And I have that piece. So if I graph this quadratic, it's in standard form, it's a little bit more work. But if I use what I just did with my square root, and knowing that my starting point is 31/4 and -3/2, I can switch that around for my quadratic, which means my vertex is at -3/2, 31/4. So I'm going to do that, and I'm going to put that up close to 8. And I'm only going to do the right-hand side so that it will be reflected over that line. But if I'm only doing that right-hand side, I need to look at the x of my vertex and restrict my domain to x is greater than or equal to -3/2. Let's try to find the inverse of the rational equation, and this was the challenge that I thought that I would offer to you. So hit pause. You can graphically check it in Desmos and give it a try. I'm going to do it with you. So we're going to switch x and y. So we have x equals 2y plus 3 over y. Notice I'm dividing by y, so I want to undo that by multiplying both sides by y. So I get xy equals 2y plus 3. I have y's on both sides, so I'm going to subtract the 2y over to get it on the same side. And then this is where kids usually get stuck. The key piece here is to factor out a y as your GCF. So y and then x minus 2 equals 3. Y equals 3 divided by x minus 2 is the inverse of this function. If we graph it in Desmos, my purple would be this piece, and then if my red would be the other piece. It's a little more complicated picture to see, but you can see that it is reflected over that line y equals x. Now we're going to look at how to do this algebraically, how to verify that two functions are inverses of each other. And this is where compositions come into play. So if I'm given f of x is 2x minus 3 and g of x is 1/2 x plus 3/2, and I want to know if they're inverses of each other, I need to do both f of g of x and g of f of x. So that means we're going to plug g into f. So I'm going to take this one and I'm going to plug it in here. Don't forget to add that -3 at the end. So this is going to equal 2 times my g of x minus 3. And I'm going to go ahead and distribute. So I get x plus 3 minus 3, and this one simplifies to x. Now we're going to do it the other way. I'm going to plug f of x into g. So f of x into g, don't forget that last term. So we're going to have 1/2 parentheses, my other grouping, 2x minus 3 plus 3/2. So when I distribute, I get x minus 3/2 plus 3/2, and this one simplifies to x. Interesting. That's what's supposed to happen. To prove or verify two functions are inverses of each other algebraically, you need to do both compositions, and if they both simplify to x, then they are inverses of each other. It has to be x and x. It can't be 3x and 2x. It can't be 5 and 5. They both have to simplify to x. How can we prove these graphically? We could go ahead and graph them. And then just a last one, are these inverses of each other? This time I'm asking you to do it algebraically, so that means compositions. So let's see if this works. I'm going to do f of g of x and simplify. So I'm going to take g of x and plug it in. Distribute, so I get x minus 8 minus 4, so I get x minus 12. So the answer here would be no, because it didn't simplify down to x. So just to recap finding inverses. When you're finding inverses, you want to switch your x and y and resolve for y. If a function fails the vertical line test, you must restrict the domain To verify graphically, the inverses will be reflected over that line, y equals x. And to verify algebraically, do both compositions, and they should simplify to x if they are inverses of each other. Good job.